Hello. So I've sort of been thinking about how the math or perfect world kind of interacts with the real or imperfect world, as I like to call it, to sort of create the fundamental ideas of the fundamental principles of science, and how that can be demonstrated through such a simple example as 1 equals 1. So in the perfect world, there are abstract concepts. So these abstract concepts, what I mean by that, is that they're basically ideas that don't exist in the real world. 93 doesn't exist in the real world. You might have 93 of something, but you don't have 93. That's an abstract concept with a certain definition. Now these abstract concepts, with their exact and precise definitions, can be put together to form a statement. Now, what is the interesting thing about a statement is that a statement can either be true or false in this perfect world. And now, whether or not this statement is true or false is of course given by the definitions of each of those concepts. And the beauty is we can go one step farther. Not only can we say whether or not this statement, given some values, is true or false, but we can actually say that in certain circumstances, this statement will always be true or always be false. So we can prove or disprove it. So in this case, this is the Pythagorean theorem, and as we know, the Pythagorean theorem is always true for right triangles. So if you measure the sides, which is A, B, and C, where C is the hypotenuse, if you measure the sides and you square each of those sides, then the sum of the shorter sides squared will be the longer side squared. And that's the case with every right triangle. There is not one right triangle that you can draw where this is not the case. So we can say with absolute certainty that a squared plus b squared equals c squared is true for every single right triangle. In the real world, we don't have that luxury. All we can really do in the real world is we can create theories, which are based on evidence, of course, but they're based on observations and basically how we perceive the real world. That's a problem, because how I perceive the real world might be different than how you perceive the real world. For example, I might see this house, the wall, to be colored blue. But you might have like a higher quality screen or whatever, and so then you see the wall to be green. So now that's a problem, because we differ on these observations. So because observations can differ, theories can't be absolute. So you can't say with absolute certainty that this house is either blue or green. Instead, what you can do is you can use models. So you can basically, well, I'll explain what a model is. And I'll actually use a very simple example. So let's say that I just built this house. And because I built it, to be honest, the walls are probably not going to be perfectly perpendicular to the ground. So we should probably measure that. And the way that I think is best to measure that is, well, first of all, we're going to need something to measure it with, a measuring tape. And then we're also going to need a certain formula that I remember back from school, which is a squared plus b squared equals c squared. So then this formula will help us with a crafty little trick, where since we know that this is true for all right triangles, if we measure a right triangle here, so where the sides are A, B, and C, then we know that this angle is 90 degrees. So for example, I could measure any length here and any length here, and then the length of the points where the two other distances ended, so that length has to be equal to C when I plug in A and B for the other two values. So for example, I value, let's say, I measure, let's say, 4 meters here, although the units also don't matter, it could be 4 feet, 4 inches, and then let's say 3 meters here. And then math happens, and we figure out that C should be 5 meters. So if I measure C and I get 5 meters, then I know it is in fact perpendicular. The wall is in fact perpendicular to the ground. If I don't get 5 meters, then, well, I screwed up and the wall isn't perpendicular. But the important thing is that in this model, we used two very important pieces. We used a real-world observation, basically, where we used the ruler to observe certain lengths in the real world, and then we used a mathematical equation or a mathematical statement that we know to be true, that is proven to be true in the cases whenever there's a right triangle. And since we used a right triangle, it makes sense to use this equation. Or since we created a right triangle. So this together gives us a basic formula, a very summarized formula of what our model looks like. So it's basically just the measured length of the wall, Pythagorean theorem, and that together, so plugging in the numbers that we measure into the Pythagorean theorem, will tell us if the wall is perpendicular to the ground or if it's not. And now that seems like a pretty stand-up model. So that then gives us the basic outline of what every model looks like, which is that factors or aspects of the real world, or I guess you can call them observations in some cases, together with laws and mechanics of mathematics, so like statements, basically just any statement of mathematics or even logic, together make a certain conclusion or prediction. Now that's the interesting part. So we made the conclusion that the house is perpendicular, or I guess if I measured like 4.9 or something meters instead of 5, then I guess we'd make the conclusion that it's not perpendicular to the ground. However, we can also predict something. So now, we didn't even measure the exact angle between the wall and the ground, and we didn't even have to. We could predict it was going to be 90 degrees or it was not going to be 90 degrees, given our model. So we could actually predict something in the real world without even doing anything. And now, of course, with bigger and more intricate models, you can predict vast things. I mean, that's basically what science is all about. Think about it. Given the acceleration and the velocity and whatever, you can predict all sorts of stuff about the kinetics of certain objects, even multiple objects, and like the three-body problem, and all kinds of stuff. And that's basically really what science is all about. So now, coming back to our problem from earlier, where we have a 1 equals 1, well, 1 equals 1 is of course true. That's just a mathematical statement, right? And given the definitions, that statement is correct. However, if we bring in the real world, so for example, if we say 1 pencil equals 1 pencil, then it gets more complicated because it depends on what aspects of the pencil we are using in this model, because this is, after all, a model. So if we, for example, say the color, the size, the function of the pencil, since they both are meant to write something with, if we use those aspects, then we can say that the statement is correct. Given those aspects, given the length of the pencil, this pencil equals this pencil. And here we use these aspects of the pencil, as we said with the model, and we use the definition of the abstract concept of what equals means. But using other aspects might not get us the same result. For example, the position of this pencil is not the same as the position of this pencil. As you can see, this pencil is way here on the left, and this one's more on the right. So given their positions, their exact positions relative to, I guess, you or whatever, or me, these two pencils are not equal. And that's really the fundamental principle of science. where scientists really the only thing they do all day is they either improve their models, they try to figure out what aspects of the real world to use and what statements in mathematics will then use those aspects, will then compute that data, and together then they form these models, and out of those models they then can make predictions about how the real world will act in certain situations. However, then some other scientist comes along and tests that model. He does exactly what the model says. He calculates what the model says the real world is going to do, and then he checks if the real world actually does that. And every once in a while it turns out that the real world actually doesn't do what the model predicted. So that means that the model is incorrect. And that means that the model has to be revised and improved. And yeah, that's basically what science does. And I mean, such a simple principle of models really goes to show how brilliant these principles are. In just about 300 years ago or so, these principles were first developed. And think about how much more we know about the universe today than 300 years ago. This constant development and improving the models to predict events in the real world really helps us learn how the real world works. So thanks for watching.